Welcome to section 4.7, optimization problems. And one of the most useful features in calculus is being able to optimize or find the optimal situation in real life circumstances. So in this section, we're going to learn exactly how to do that. We're going to follow a 6-part strategy. First, read the problem carefully. Second, draw a diagram whenever possible. 3, you want to introduce notation, so start labeling quantities in your diagram as well as including derivatives when necessary. 4, express the quantity to be optimized in terms of other variables. This is very important. 5, reduce the number of variables from step 4 to only one. We need to write our function of only one variable. And then step 6, find the absolute min or max, and we're going to follow the techniques from earlier in the chapter with how we found the mins and maxes for various functions. All right, so to begin with, we're going to look at a nice example that's pretty straightforward. Find two numbers whose difference is 100 and whose product is a minimum. All right, we read that pretty carefully. There's no diagram to draw, so let's just start introducing notation. So we're trying to find two numbers. It seems natural that we would let those two numbers be x and y. And let's continue reading and see how we can translate and introduce math notation. It says the difference of these numbers is 100. Well, how would I express that? Their difference, x minus y, is or equals 100. And then the last part of the problem states we need to find these two numbers whose product is a minimum. So their product, let's call it P, that would be the product of x times y. This is the quantity that I'm trying to minimize, okay? So whatever quantity you're going to try to minimize or maximize in these optimization problems, that's the function whose derivative you're going to need to take because you're going to find the critical values and apply the techniques from earlier in the chapter for finding minima and maxima. Now, we're in calculus 1, calculus of functions of one variable. So whatever I'm trying to minimize or maximize needs to be a function of only one variable. So here, we're going to focus on this equation and reducing the number of variables. That way I can go ahead and take its derivative. And you're always going to be given some other piece of information in the problem that will enable you to do this. In this case, it's the fact that the two numbers have a difference of 100. So at this point, it's up to us. We can either solve for x or solve for y. The way we've set things up, it's pretty easy to solve for x, right? So we have x equals y plus 100. And so now I'm going to substitute that in for x into the equation. So now I have p, which is going to be a function of y, is equal to y plus 100 times y. All right, and you want to make sure you introduce that function notation. So p of y, when I distribute, is going to be y squared plus 100y. So now my function is all ready for me to minimize it. I can go ahead and take the derivative. So p prime of y is going to equal 2y plus 100. All right, well, I get critical values from two places, either where p prime of y is equal to 0 or where p prime of y does not exist. Make sure you always list and consider both cases. Well, if p prime of y is equal to 0, that would mean that 2y plus 100 equals 0, which would mean y equals negative 50. What about where p prime does not exist? Well, there's none from that case, right? We see that p prime is a polynomial. It's a linear function, so it doesn't have any restrictions. So right now, I obtain the value of y equals negative 50. But this is just a critical value. I need to confirm that this will indeed yield a minimum. Now, earlier in chapter 4, a lot of the time, in order to confirm if a critical value was a local min or max, we used the first derivative test and made a number line listing the critical values and tested where our function was increasing and decreasing. A lot of the time for optimization problems, it's more straightforward to apply the second derivative test. So now's your chance to use it. Make sure you don't forget this part because it's essential in every single optimization. So we need to check if y equals negative 50 indeed yields a minimum. So remember, according to the second derivative test, if I know my critical value evaluated in the second derivative comes out to be positive, that means my function is concave up there, so that critical value is a min. So let's first compute p double prime of y. And here's p prime of y, so p double prime is just going to be positive 2. And that's not even a function of y anymore, it's just a constant. And this is always positive, which means my function p is concave up. So it looks something like this, which means at y equals negative 50, that critical value indeed yields a min. Okay, in order for you to receive full credit on a problem, you must include this step of checking. Okay, well, the problem asked us to find two numbers. I have one of them. I have y, and remember, right here we know x equals y plus 100. So we can go ahead and find x. X is going to be y, which is negative 50, plus 100, which is 50. And then in this case, I want to write my answer out as a complete sentence. The two numbers are 50 and negative 50. All right, very nice. Let's box that, and then we can move on to some examples that are a little more interesting. All right, next problem. A rectangular storage container with an open top is to have a volume of 10 meters cubed. The length of its base is twice the width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for the cheapest such container. All right, well, first things first, we read it pretty carefully. We're trying to find the cost of materials for the cheapest such container. So let's draw it out and then figure out what sort of quantity we're trying to, in this case, cheapest means minimize, right? You want to minimize the cost. So we have a rectangular container, and it's open. Okay. And it's a very special container because the length of its base is twice the width. So we can label those sides whatever we want. Let's say this is the width, then the length is going to be twice that, or 2x. And then we don't know anything about the height, so I'll just call it h. All right? Well, they told me here in the beginning of the problem that the volume was 10 meters cubed. Okay, so the volume is 10 meters cubed. And now we have a little bit more information here. The material for the base costs $10 per square meter. So that's $10 per meter squared, per square meter for the base. The material for the sides costs $6 per square meter. So sides are $6 per meter squared. So find the cost of materials for the cheapest such container. So you're trying to minimize cost. And what is the cost based on? The cost is based on the surface area of this open rectangular storage container. Okay, so I'm going to build a cost function. Let's call it C. And I'm going to have to take the cost of the making material for each of the sides. Now, how many sides are there going to be? Since it has an open top, I just have one base, and then I have 4 sides. Okay, so let's build this cost function. First of all, the cost of the base is going to be the area of the base. Well, what's the area of the base? It's going to be the length times the width. So that's going to be 2x times x. And then what's the cost for the materials for the base? Well, it's $10 per meter squared. So I'm going to multiply this by 10. So this is cost of the base. Now, I have 4 sides, but notice they're not all identical. So we have the front and the back. They have the same dimensions. What are their dimensions? Well, it's going to be h by x. So h by x. How much do those cost? Well, they cost $6 per square meter. And remember, I have 2 of them, one on the front, one on the back. So this is cost of front and back. Plus, then we have the sides. So the sides are going to be this long side here and the one back here. Now, if you label things differently, it's fine, as long as you just set things up in the proper order and proportion. Okay, well, what are the dimensions of those sides? It's going to be h times 2x. They again cost $6 per square meter, and there's 2 of them. So this is the cost of the sides. Now let's simplify and clean things up a bit. So we have c equals, that's going to be 2x squared times 10, so 20x squared, plus this is going to give me a 12xh, and then I have another 12 times 2, so 24xh. So altogether, c equals 20x squared plus 36xh. All right, now remember, whatever function you're trying to minimize is the function whose derivative you're going to take. And we're in Calc 1, so I can't have a function of more than one variable. I need to get rid of either x or h. Well, that's why they gave me that information in the very beginning, the constraint, that the volume had to be 10 meters cubed. That's going to help me eliminate one of the variables in my cost equation. All right, well, how do I express the volume for this rectangular container? Well, the volume is the length times the width times the height. So that's going to be 2x times h, which means that 10 is equal to 2x squared h, which is the same if I divide by 2 as saying 5 equals x squared h. And let's decide, is it going to be easier to solve for h or to solve for x? Well, for sure h. So h is equal to 5 over x squared. And now this is the key to me rewriting my cost equation as a function of just one variable. So I'm going to substitute 5 over x squared in for h. And now I can write c as a function of x. Make sure you include that in the next step, once you've reduced everything to one variable. So we're going to have 20x squared plus 36x times 5 over x squared. And so c of x is equal to 20x squared plus 180 over x, right? One of those x's is going to cancel out. All right, now let's go ahead and compute c prime of x. So c prime of x is going to be 40x. Remember, this is 180 x to the negative first. So the derivative is going to be negative 180 over x squared, right? X to the negative second. And then in order to find critical values, I want to write my derivative with a common denominator. So it's going to become, multiplying the first term by x squared, 40x cubed minus 180 over x squared. All right, so here's our derivative. Now we're going to use that to find critical values. So I want to check where c prime of x equals 0, as well as where c prime of x does not exist. Okay, if c prime of x equals 0, that means the numerator is 0. So that would mean 40x cubed minus 180 is 0. So that would mean x cubed is 180 over 40, which is 9 over 2. So that means x cubed, or x, now let's just go ahead and take the cube root now. So x is the cube root of 9/2. All right. Now we're going to leave that here. You can think of it also as the cube root of 4.5 if that makes it a little bit easier. What about where c prime of x does not exist? Do I get any critical values from there? Well, that would be if x equals 0, but that's not in the domain of this problem, right? Why do we say it's not in the domain? Well, obviously you're going to minimize cost if x is 0 because you're not even making a box at all. So that would be the cheapest outcome. But we have to make a box, so x equaling 0 is not a legitimate solution in the context of this problem, so we say it's not in the domain. All right, well, now that I have my critical value, what do I need to do? I need to confirm that this yields a minimum. And in order to do that, I'm going to apply the second derivative test. So I'm going to indicate that I'm doing that. I need to check if x equals the cube root of 9/2 indeed yields a min. So I'm going to compute c double prime of x. And the best place to go to compute it is from right when we computed c prime before we got the common denominator. That way you don't have to do any nasty quotient rule. So this is going to give me 40, and then I'm going to end up with now a positive, if I multiply by a -2, positive 360 over x cubed. All right? And so c double prime of my critical value, the cube root of 9/2, is going to be 40 plus 360 over, if I cube the cube root of 9/2, it's just going to be 9/2. And honestly, I don't care what value I get. I just want to know if the second derivative is positive or negative at that critical value, and I can already tell that it's positive. So that means the function is concave up when x is the cube root of 9/2, which means that it yields a min. Okay, now let's answer the question. The problem asks us, don't forget, what did they want? To find the actual cost of the materials. So they want us to find what C is. So I'm going to substitute this value of x into my cost function. Remember, my cost function is right here, 20x squared plus 180 over x. So we'll just fit that in right here. So C of the cube root of 9/2 is going to be 20 times the cube root of 9/2 squared plus 180 over the cube root of 9/2. And then from here, we're just going to substitute everything in our calculator, and we'll round to the nearest penny. That's what makes sense here. So this is approximately $163.54. All right, that's our final answer. Nice job. All right, last one. Find the point on the line 6x plus y that is closest to the point -3, 1. All right, let's draw a graph of this line. So this is the equation of y equals -6x plus 9, right? So we have a line with y-intercept positive 9, and the slope is -6. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's y, here's x, 1, 2, 3, -1, 2, 3. All right, so I have y-intercept here, and then the slope's -6, so I can go down 1, 2, 3, 4, 5, 6, and then over 1 to the right, just to give us an idea of what's going on. And then the point is -3, 1. Okay, so I need to find a point that's on this line that's the closest to this point here at -3, 1. So there's infinitely many points on the line, right? Here's a point on the line, here's a point on the line, here's a point on the line, so on and so forth. Which one's the closest? Well, later on you're going to learn that it's the one that's perpendicular if you connect it, but we need to find the coordinates, not just eyeball it using a graph, okay? So remember, in optimization, you first have to figure out, are you trying to maximize or minimize a quantity, and what is that quantity? Well, translate the word closest. Closest means minimum distance. So our goal is to minimize the distance from our point, -3, 1, to the line. Okay? Well, we have a distance formula in math. Isn't that convenient? So the distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, when x1, y1, and x2, y2 are 2 points. Well, I know I can use -3, 1 for one of my ordered pairs. What about the other one? Well, I don't know what point on the line is going to be the closest. It's some arbitrary x, y. But since I know it lies on the line, I can express that ordered pair as x comma -6x plus 9, right? Since it must satisfy the equation of the line. So that's what I'm going to use here in the distance formula now. So the distance is going to equal the square root. I'm going to have x minus -3, so x plus 3 squared, plus, and then instead of y2, I'm going to use -6x plus 9 minus 1 squared. All right? Then let's start cleaning things up a little bit. So d equals the square root. Quantity x plus 3 squared is going to be x squared plus 6x plus 9 plus, and then let's see here, this is going to be, just so we save a little bit of time, this is -6x plus 8 squared. So that's going to give us plus 36x squared minus 6 times 8, that's 48 times 2, so it's -96x plus 64. Beautiful. And then I can combine like terms. So d equals the square root of 37x squared. 6x -96x, that's minus a 90x, plus 9 and 64 is 73. Okay, so here's our distance formula, and this is the quantity that I want to minimize. If I want to minimize it, according to our techniques from earlier, I need to take the derivative of this function. Now this is not going to be the easiest derivative to take because we have a radical function and I'm going to have to apply the chain rule. So what we're going to do, and this is a technique you can apply during optimization problems when you have a radical function, we're going to let capital D equal my distance squared. So basically, capital D of x is equal to 37x squared minus 90x plus 73. Everything underneath the radicand, but no square root sign anymore. Well, as a note, whatever x value minimizes lowercase d also minimizes this new function capital D, which is d squared. And this is an easier function to work with, as I'm sure you guys can all see. Okay, so we're going to go ahead and use capital D of x, which is 37x squared minus 90x plus 73. All right, so let's take the derivative. So d prime of x, 37 times 2, that's 74x minus 90. Now I want to find my critical value, so I want to see, all right, where d prime of x equals 0, as well as where d prime of x does not exist. Well, d prime of x equaling 0 would mean 74x minus 90 is 0, which would mean x equals 90 over 74. D prime of x does not exist. That doesn't ever happen. Again, it's never undefined, so there's no values there. 90 over 74, I can reduce that, right? Divide by 2, that's going to be 45 over 37. All right, so now I have my critical value. What do I need to do? I need to check or confirm that x equals 45 over 37 yields a min. And I'm going to use the second derivative test to do that. So d double prime of x. Here was d prime of x. So the second derivative is just 74, which is a constant, so I don't have to plug in x anywhere. I can tell right now it's positive, which means it's concave up. So our x value yields a min. All right, that's great. Now, did we answer the problem? Let's go back and check. The problem asked us to find the point on the line. Well, so far I just have the x coordinate. I don't have the y coordinate. Where do I get the y coordinate from? The equation of the line. Since this point lies on the line, the y coordinate is going to come from just substituting in 45 over 37 for x. So here we go. Y is going to be equal to -6 times 45 over 37 plus 9, which is 63 over 37. So the point has coordinates 45 over 37, 63 over 37. That's our final answer. All right, if you're curious what that is as a decimal, it's approximately 1.22 for the x coordinate and 1.70 for the y coordinate. And let's go back to our graph and just make sure that visually this sits right with us. So 1.22, 1.70, I'm just gonna scroll back up. I'll do it in red so it stands out. 1.22 and 1.7 looks like it's about here. And indeed, if I drew a line from -3, 1 to our line, it looks like that's the shortest one. And if you found the equation of this line, just as a fun extension, you can confirm that this line is going to be perpendicular to our line. So it should have a slope of +1/6. All right, that concludes the section. Comment down below if you have any other questions or video requests, and be sure to subscribe so you get notified every time I upload a new video.